You students, actually, in this thing, we will study about the electric fields due to continuous charge distributions. Because in the previous lecture, we have studied how an electric field is formed by charges at a particular point. That is, you have point charges. You have charge Q1, Q2, and so on at different points. And you want to find out the electric force at a particular point where you have a charge, a point charge, or an electric field at a particular point. That's what we have studied. But in this lecture, what we are going to study is, instead of, for example, you have a point charge like this. This is a point charge, right? And like a point charge, you can have a line charge like this. The charge is distributed along the whole line. Okay. And you can talk about a line charge density of rho L coulombs per meter. That means if you take 1 meter of that particular line, it has a total charge. It has a charge of rho L coulombs per meter. Every meter of it is having rho L coulombs, right? Similarly, you can have a surface charge. You can take a surface like this, and on the whole surface, you may have charges. And you can talk about a surface charge density. This is line charge density, right? Rho L. Rho L is line charge density. That is rho L. And here you have surface charge density. On this you have a surface charge density, about which you can say it is surface charge density is given by a particular value rho s coulombs per meter square. Similarly, you can even think of a volume like this, the volume, and in the whole volume you can have charges distributed over the whole volume, right? And here you can think about a volume charge density. You can think about a volume charge density given by rho v coulombs per meter cube, because it is volume, right? So it is not just a charge at a particular point. You can have a charge distributed along a line or a curve or whatever it is, and you can have a charge distributed in an area or a surface, and also you can have a charge distributed through a whole volume. So instead of talking about a single charge Q coulombs at a point, you can think about coulombs per meter square, and coulombs per meter cube. Okay. So first we will study about a line charge. So I'll draw a diagram here. You can see. So this is our y-axis. Okay. This is our x-axis. This is our z-axis. Right. And now I will mark a particular point like this. I can have this point is A, okay, and this point is B, okay. And what I do is, now I will select a particular point. Okay, let us have a point here. Let us draw a vector from here to here, from here to here. Then I think this I'll draw it more clearly, then it should be clearer. we will have the y-axis going on like this. This is the y-axis. This is the x-axis. And this is the z-axis. And on this, I will select a particular line charge in the z direction. This is y, x, and this is z. So I will choose this point as A and this point as B. So there is a line charge starting from A and ending at B. And suppose if I have a point here, okay, I will take that point P. I will have that point P. Now I can draw a line like this. And I can draw another line like this. Okay. And I can draw a perpendicular from the z-axis. A perpendicular from the z-axis to this point. Okay. Now I can choose a small element of length here. That element of length is given by dl. It is in the x direction. You can say it is dz. No problem. Okay. Now the charge, the total charge in the length dl. Okay. Total charge in the length dl is given by charge in length dl is equal to dq. Okay. Equal to rho l dl. Isn't it? So that's how you have the thing. Now what I will do is I will have this angle given by alpha 2 and this angle is given by alpha 1. Okay, I am not going into the derivation of this particular equation. Okay, the electric field in this case is given by, we can write the equation for the electric field like this: E equal to rho l by 4 pi epsilon 0 rho, and you can have minus of sine alpha 2 minus sine alpha 1 a rho plus, okay, cos alpha 2 minus cos alpha 1 AZ 0, this is AZ. That is how you have the equation for the electric field for the case. This is the length rho. Okay, so the length rho, the length from here to here is rho. This is the point P. Point P, you can have the point X, Y, Z, whatever it is. So this length rho, you see. So that is how you get the electric field due to this particular line charge extending from point A to point B. Now suppose if you have the line extending from minus infinity to plus infinity. So it is A is going down to minus infinity on the z-axis and B is going up to plus infinity on the z-axis. In that case, you can write E equal to, as infinite line charge, you can write E equal to rho L by 4 pi epsilon 0 rho 0. Okay. Rho L by 4 pi epsilon 0 rho 0. That's the equation for the electric field. Understand? This is E equal to, you can write it once more clearly, E equal to rho L by 4 pi epsilon 0 rho 0. Okay. The case is like this. You have a line charge extending from minus infinity to infinity. You have a point P here, and this point P is at a perpendicular distance of rho. Okay, this is the point P from the line charge. Okay, and the line charge has a density of rho L coulombs per meter. Okay, and arrow, you know, this is the direction of arrow. Arrow is a unit vector in the direction of rho, isn't it? So this is how you can determine the electric field intensity due to an infinite line of charge. Okay. Now we'll do the thing for a surface charge. Okay. What I have done is, again we will do the thing in the XYZ axis. This is the Y axis. This is the X axis, and this is the Z axis. And I have a surface like this. This is a surface. Okay. And I assume that this surface is in the XY plane. This surface is in the XY plane. And the charge density is given by, you can say the charge density is given by rho s coulombs per meter square. That's the charge density. Charge density. That's the density is coulombs per meter square. Now, suppose if I take a particular point P, I'm taking a point P on the Z axis. Okay. Now, the electric field is given by rho s by 2 epsilon 0 A n, where you can see this is the particular point P. This is the direction of AF. AN is in the direction of Z. Okay, you can say in this case AN equal to AZ. Okay, if the surface charge is in X plane, XY plane, in xy plane, then AN equal to AZ. If it is above the xy plane, if it is below, it is minus AZ, like that. Okay. Suppose if the surface charge is in the xz plane, AN will be AY. If the surface charge is in the YZ plane, AN will be in the direction of AX. Right. So that's how you do it. And you can also see that it does not depend, this electric field intensity does not depend on the distance of the point P from the xy plane. The distance is not important. Okay. So that's how you have the thing. We'll see another example. For example, I have one surface like this. For example, I have a surface like this. This is an xy plane. Okay. I have another surface also here. Okay. Now I have a point in between these two surfaces, right? And I will take this direction as the direction of AN, and obviously this direction will be minus AN, isn't it? If this direction is AN, the other direction will be, this will be minus AN, isn't it? This is minus AN. This is direction AN. Okay. Upward direction is AN. Upward direction is AN and downward direction is minus AN. Okay. So I have a point here. This is the place where you have the point P. Understand? Suppose this is having a charge density rho s. This is having a charge density rho s, and this is having a charge density minus rho s. Okay. Now this is having some positive charge. This is the lower plane is having a positive charge, and the upper plane is having a negative charge. So it is something like a capacitor. It's looking like a parallel plate capacitor, right? Parallel plate. You can say this is like a parallel plate capacitor. The capacitor that we study normally. You know about the capacitor, right? Like this. This is the capacitor, isn't it? Like that. One is plus, another is minus. Here you have a charge density of rho s, and here you have a charge density of minus rho s. You have some point in between. You want to find out the electric field at that point. So you can write the electric field equal to E equal to, okay, if you take the lower plane, xy plane, it is having an electric field of rho s by 2 epsilon 0 AN. And if you take the upper plane, it is having something like minus rho s, right? And you have minus AN divided by 2 epsilon 0. So if you add both of them, you will get the electric field at any point in between the two plates as rho s by epsilon 0 AN. Right. So the electric field is, you can see the direction of the total electric field is in the AN direction, that is from the plate with the positive charge to the plate with the negative charge. So in the capacitor, in between the two parallel plates, you have the electric field such that the electric field starts from the plate with the positive charge and ends at the plate with the negative charge. That is how you have the thing in the case of two parallel plates, parallel plate capacitor with two plates charged with positive and negative charges. So now we will see the case for a volume charge. So in the case of a volume charge, you will see Suppose you have a volume, I will draw a sphere here. This is the y direction. This is the x direction. And this is the z direction. And then we will draw a sphere like this. Okay. You can draw it more clearly. Okay. Anyhow, something like this. Yeah, sphere like this. So the perfect sphere that I have drawn, but still think that it is a sphere. And I have some points somewhere here. Okay, so I can say that point is given by P. Any point anywhere. Okay, you can have any point here, maybe here. No problem. This point is given by P, R, theta, phi, the spherical coordinates. Okay. And this is the sphere, and this sphere actually is having a charge density of rho v coulombs per meter cube. Understand? And I have the distance to this point. Okay. The distance to this point is given by r, isn't it? See. So in that case, you can say that the electric field at the point PR theta phi at point P R theta phi is given by E equal to Q by 4 pi epsilon 0 R square AR. AR is this direction. AR is in this direction. Okay, this is the direction of AR. This direction. This direction. That is the direction of AR. Now we will do a simple problem. Okay, I will do the problem for this surface charge and a line charge. Okay. So we have a plane, two planes. We have an example here. Two planes. X equal to 2 and y equal to -3 respectively. Carries charges carries charges and coulombs per meter square and 15 coulombs per meter square. And if the line was a line x equal to 0, z equal to, that's a single line. And calculate E at 0.11 minus 1 because of the charges. So you can have the total electric field E is given by E1 due to plane x equal to 2. Okay. This is because of the plane x equal to 2. And E2, E2 due to y equal to minus 3 plus E3 due to the line charge. Okay. So I will write E1 is because of the surface charge, right? So I can write it as rho S1 by 2 epsilon 0. Okay, I will write it as A1, for example. Okay, I don't know what is the direction of A1. Similarly, you can write E2 equal to rho S2 divided by 2 epsilon 0 A2. Okay, I don't know the direction of A2. And E3 you can write as, because it is due to a line charge. E3 is due to a line charge. You can write it as rho L divided by 2 pi epsilon 0 rho A rho. Okay, so we have to find out what is A1, A2, A rho, and all those stuff, right? Now you see how these three things are there. I can draw them like this. See, this is the y direction, this is the x direction, and this is the z direction. Okay, so we have three planes, right? What are the two surfaces are there? One is the surface x equal to 2, right? So I can have the surface, this is x equal to 1, this is x equal to 2. So I have a surface going on like this. I have a surface going on like this, right? This is a surface that I have. Okay, I have the surface like this. This is the surface. You can call this surface. You can call this surface as x equal to 2, right? This particular surface. And the other surface, you can say it is in the minus. It is in the minus y direction, right? This is y equal to minus 1, y equal to minus 2, and you can say this is y equal to minus 3. Okay, this is y equal to minus 3. So I have a surface there. I will write in a different color. Okay, so I have the surface going on like this, right? Right. the y equal to this surface is the surface y equal to -3. It's an infinite surface. X equal to 2 is an infinite surface, and y equal to -3 is also an infinite surface, right? So these are the two surfaces, and the third one is a line, isn't it? What is that line given by? Line is given by x equal to 0. X equal to 0. You see x equal to 0 is here, and z equal to 2, z equal to 1, z equal to 2, right? Then y can be any value. So this line, I can put it in the red color, right? So I have a line like this, isn't it? So for this line, you see, for every point z equal to 2, then x equal to 0, right? So this is the line x equal to 0, z equal to 2. Y can take any value, right? Now where is the point 1, 1, minus 1? We have to calculate the thing as the point 1, 1, minus 1. So this is 1, 1, 1, and z is minus 1, right? Okay, so you have the point here. This is the point p equal to 1, 1, minus 1. So I have to calculate the electric field at that particular point. You see, if you take the x equal to 2 plane, for the point P, x equal to 1, right? From the plane x equal to 2, and the point is P 1, 1, minus 1. For that x equal to 1. So from x equal to 2 to x equal to 1, okay, so you have to say that the direction of A1 is from x equal to 2 to x equal to 1. So it is in the direction minus ax, right? From larger value of x to smaller value of x, it is in the negative x direction, right? Similarly, if you take the case of the unit vector a equal to 2, you see it is from, if you take that plane, it is from y equal to -3 to y equal to 1. Smaller value of y to larger value of y. So it is in the AY direction, right? So you can say A2 equal to AY, right? Understand? Now, what we will see, what is the E1 and E2 now you can calculate. It's simple. E1 is rho S1 to epsilon 0 A1, right? So you can write E1 to rho S1 by 2 epsilon 0 A1, right? So this is rho S1 by 2 epsilon 0. Now what is the direction of A1? Yes, the direction of A1 is minus AX, isn't it? That is minus, you can put a minus here, AX, right? And E2 you can similarly write as rho S2 divided by 2 epsilon 0 AY, isn't it? Now this is, what is rho S1? Rho S1, the value is 10 into 10 raised to minus 9, right? Here it is 10 into minus of 10 into 10 raised to minus 9 divided by 2 into 10 raised to minus 9 divided by 36 pi and AX. It will be, you can write it as minus 180 pi AX. Similarly, you can write this thing as 15 Okay, 15 into 10 raised to minus 9 divided by 2 into 10 raised to minus 9 by 36 pi AY equal to 270 pi AY. So like that you can get A1 and A2, right? Now we have to find out what is A3, right? Now how to find out A3? See, A3 is from the line, see, x equal to 0, z equal to 2, right? Understand? So x is fixed 0, z is also fixed 2. I have to find out the distance from that line to the point P1, 1, minus 1. You cannot change x, you cannot change z, but you make y same. You take a point on the line x equal to z equal to 2 where y equal to 1. Because the point P also is having y equal to 1. Okay. Then you can find out the distance like this. Okay. Then it is very simple to find out the distance. Okay. So you have to find out, for example, E3. What is E3? E3 is, right? You can write E3 is equal to, what is it? E3 equal to rho L by 2 pi epsilon 0 rho 0. Right. So first we will find out what is rho. Okay. So you can find out rho, vector rho. Okay. What I said is on the line x equal to z equal to 2, you take the point where y equal to 1, because that point P also is having y equal to 1. Okay, so you have the point 0, 1, 0, 1, 2. Okay, so we have 1, 1 minus 1 minus 0, 1, 2. Okay, 1, 1. Write it as 1, 1 minus 1 minus 0, 1, 2. Zero, 1, 2, right. So you can get it as 1, 0, minus 3. So you can write rho equal to 1, 0, minus 3 divided by square root of 1 square plus 9 square, that is square root of 10, isn't it? Now you can find out what is E3. You can write E3 equal to 10 pi, right? Coil into 10 raised to minus 9 divided by 2 pi epsilon 0, that is, into 10 raised to minus 9 by 36 pi into rho. What is rho? Magnitude of rho, right? Rho is magnitude of rho equal to square root of 10. Okay, so you have 10 here, then you have again square root of 10 here, then you have 1, 0, minus 3 divided square root of 10 again. So altogether it will become 18 pi AX minus 3 AZ. So total electric field, you can write it as, the total electric field is given by E equal to E1 plus E2 plus E3 is given as minus 162 pi AX plus 270 pi AY minus 54 pi AZ volts per meter. That's how you find out the electric field. sir.